Hi, and thank you for joining this session. My name is Nadia Carlston. I'm a Senior Product Manager in the Quantum Computing Group, and today I'm excited to tell you more about quantum computing on AWS with Amazon Braket. Amazon Braket recently launched as a generally available service and is designed for customers looking to get started with quantum computing. In this presentation, I will tell you more about where we are in this exciting field of quantum computing, give you an overview of key features of this new service, and walk you through a demo on how to start using it. By the end of this session, you should have a good understanding of what is possible with Amazon Braket and even be able to send your first quantum task to a simulator and quantum hardware of your choice. There's a lot of opportunity around quantum computing, but also a lot of hype. So let's start by getting all on the same page about where we are with quantum computing today and what some of the challenges are. Quantum computing takes advantage of quantum mechanics to perform computation in new ways. And this means that a quantum machine operates on a very different set of rules than a classical computer. The reason there's interest in this is because of the potential of this new type of computing to really speed up solutions to hard problems. The idea is that by taking advantage of quantum mechanical properties, we can expect exponential performance improvement, and that in turn would enable us to solve problems that are otherwise impossible. That being said, quantum hardware at scale is still a tough problem, with a lot of scientific and engineering complexity. There are many approaches that the quantum community is still exploring to build better and more reliable quantum computers. And later in this talk, I would go over the different types of quantum hardware that are currently available through Amazon Braket. But currently, we are still in what is referred to as the NISQ era, noisy intermediate scale quantum computing. And NISQ devices are limited in two ways. They have limited size, measured in terms of number of qubits, and this affects the size of the problem or the computation a device can perform. But they're also limited when it comes to the quality of the results. Noisy emphasizes that we have less than perfect control over these qubits. To get a visual representation of what I just mentioned, we can just plot error rates, which is a measure of the noise in the system, against the number of qubits. A low amount of noise means better quality, and having more qubits expands the range of problems that we can solve with quantum computers. So we obviously want to be in the blue area to the right. At the other end of the spectrum, we are in a situation where simulators, based on classical hardware, are actually better than quantum computers. This is generally below about 50 qubits or so, or even at higher number of qubits, but when the error rates is very high. In this situation, we have quantum systems that may be interesting, but they cannot perform better than classical computers. Today, we are at the intersection of 1 and 2. We are entering the NISQ era. We have indication that quantum systems can do computations that classical computers cannot, but we don't have proof yet that they provide an advantage when it comes to useful problems. The ultimate goal is fault-tolerant computers that can run useful quantum algorithms reliably. To get there, we'll have to increase the number of qubits as we improve the quality of the qubits through error correction. This is where we expect quantum computers to outperform classical computers, and where there will be a provable advantage. In the meantime, we have to keep exploring useful applications that can make the best use of NISQ-era devices. As I mentioned, the ultimate goal of quantum computing is to speed up how we find solutions to very hard problems, even problems that currently cannot be solved in any other way. So you might be wondering, which fields or industries have the potential to benefit from this speed up? Based on previous research, we know that quantum computing can be a potential game changer for several different application areas, including computational chemistry and materials science. The reason there's a lot of interest in these fields that require studying properties of quantum systems is that there's no machine better suited to solving quantum mechanical equations than a machine that operates on the very laws of quantum mechanics. Another field where quantum computing has a lot of potential is optimization. And the reason is, when you're trying to find the optimal approach from a set of options, as you increase the number of possible combinations, the complexity of the problem scales up very quickly and overwhelms a classical computer, even a supercomputer. Quantum computers, on the other hand, can take advantage of superposition, so they are able to explore the possible configurations simultaneously, creating a huge speedup. This can be useful for many types of optimization problems, from optimizing portfolios for financial services applications to network optimization for logistics and supply chain management. However, we have to keep in mind that achieving this potential requires fault-tolerant quantum computers. We have to recognize the fact that the number of physical qubits required for practical applications is in the range of hundreds of thousands of qubits, and we're still a long ways from that. So a natural question, especially considering some of the limitations of the devices that I just described, is why even care about quantum computing now? We believe that by bringing quantum computing out of the lab and into the hands of customers, we'll see a virtuous cycle that will help accelerate innovation in the quantum community. Similarly to how machine learning really took off once developers and researchers had easier access to powerful compute and more data. We expect that as hardware capabilities continue to advance, users will be interested in trying out the different options, which in turn will help identify more use cases and algorithms suited for quantum. And that in turn will incentivize hardware developers to really push the limits of hardware capabilities. We also believe that now is the right time for customers to prepare for quantum by figuring out how it can be applied to their use cases and how they can start to build up expertise and develop competencies in this field. In addition to Amazon Braket, our approach for quantum computing includes a couple more elements. The first is the AWS Center for Quantum Computing, which is being established at Caltech. As I mentioned before, quantum computing is a very nascent technology, and a lot of innovations will be required to make the technology viable. The center will bring together researchers and engineers from Amazon, along with leading academic institutions, to research near-term applications and work on developing better tools. Second, we have the Quantum Solutions Lab, which is a professional services program that allows customers to work with Amazon experts in quantum computing, machine learning, and HPC to dive deep into promising near-term applications and use cases, and collaborate with experts on developing new algorithms and approaches. And of course, Amazon Braket is the third element, an AWS service that makes it easy for customers to get access and start working with quantum computers. So Amazon Braket is a fully managed service, taking away the complexity so that customers can experiment with quantum computers with an easy, on-demand model. We provide fully managed development environments so that customers are not restricted to device-specific frameworks when they're designing and building quantum algorithms. Amazon Braket also provides hosted, high-performing circuit simulators so that customers can test quantum circuits on classical hardware. The advantage of a managed simulator is that it takes away a lot of heavy lifting that would otherwise be required to configure and manage the underlying compute infrastructure to get to the best performance. And finally, Amazon Braket gives you secure on-demand access to different types of quantum computers, all from one interface. This ability to explore and execute tasks on different types of quantum computers is something that we hear from customers really helps to make experimentation a lot easier. Amazon Braket makes it possible to access 3 leading types of quantum computers from 3 different hardware providers that have partnered with Amazon Braket. Customers have access to a quantum annealer from D-Wave, a trapped ion computer from IonQ, and a quantum processor based on superconducting qubits from Rigetti. All of these devices are securely integrated with the AWS service and easy to access through a common interface, making it easy for customers to swap which device they want to use for their computation and try out different technologies. So let's take a look at what a typical customer workflow is for Amazon Braket users. To get started, you can choose to use Amazon Braket notebooks, which are fully managed Jupyter environments. As I'll show you in the demo, you can launch notebooks with a simple click in the console and start working right away. The notebooks are pre-installed with the Amazon Braket SDK, which is a programming framework that is hardware agnostic, and that makes it easy to develop circuits and problems to run on Braket. Once you've defined your algorithm, you can run your quantum tasks on either simulators or actual quantum hardware. Simulators are important because they enable you to test your approach in a cost-effective way when you're at the stage of still validating your circuits. And of course, our managed simulator is optimized for AWS infrastructure to give you the best performance. Then you can choose which quantum service to use and run your algorithm on real quantum hardware. And you can switch between devices with a single line of code. The results are returned to you in your Amazon S3 bucket that you control in your account, so you always have the results to work with and do further analysis. And because Amazon Braket is integrated with additional AWS services, you'll also be able to take advantage of things like Amazon CloudWatch for monitoring and AWS Identity and Access Management, so you can manage roles and permissions in your account. So with that in mind, let's go to the demo, where I'll show you how to get started with Amazon Braket. So starting from the AWS Management Console, the first thing you'll want to do is check which AWS region you're working in. Amazon Braket is currently available in 3 regions: US East 1, US West 1, and US West 2. You'll want to pick one of these 3 regions to be able to work with Amazon Braket. From the list of available technologies, Amazon will be under the quantum computing category. Clicking on Amazon Braket from this AWS console will take you to the Amazon Braket service page. On the service page, you'll find general information about some of the benefits and example use cases of Amazon Braket. There's also links to resources, such as information about pricing, documentation like the developer guide, info about hardware, and an FAQ section. Clicking Get Started takes you to the onboarding step. Now, one thing to note is that you only have to do this onboarding step once to set up your account the first time you use Braket. One of the things to do here is pick where you want your results to be stored. There are 3 options. You can specify a new Amazon S3 bucket by entering a name, or if you happen to have a bucket already created, you can select it, or you can simply use the default to create a new one. Amazon Braket creates a service-linked role in your account. This is what allows Braket to access AWS services. Here you can review the permissions attached to the role, and to learn more about service-linked roles, you can also check the documentation. Finally, Braket makes it possible to access devices provided by third-party quantum hardware providers, so those quantum tasks will be processed outside of AWS. Review the terms and check the box. And that's it. Once you've completed these simple steps, you can start using Amazon Braket. Now let's take a look at the devices you can work with Amazon Braket. Once you've set up your Amazon Braket account, you can get started with the service. And this page is one of the landing pages that shows you all of the devices you can work with. There are quantum processing units, or QPUs, those are the quantum hardware, as well as a circuit simulator that is available for circuits up to 34 qubits. Each device card gives you information about the QPU, including the type of hardware it is and its provider. You can also see the status of the device, which tells you whether the device is online or offline, which AWS region the device is associated with, and you can also see if the device is currently available to process tasks. If it's not, you'll see a countdown clock, like here for IonQ. Now I'm looking at one of the QPUs to get more details. So here I get a description of the QPU available from Rigetti, which is the Aspen 8 chip. I have some additional info about the device, also something called the device ARN. That's what we'll use in the SDK to identify the device. You can also see the topology of the device. In the case of Aspen 8, it's a 32-qubit architecture based on an octagonal geometry, which gives the device a distinctive connectivity map. Here you can also see the calibration data of the device, which includes fidelity, coherence time, and other data you'll find useful when planning your experiments. Now let's take another look at a different device. So this is the QPU from IonQ, also a gate-based quantum computer, but this one is based on trapped ions. Ions are confined using electromagnetic fields, and lasers are used to perform gate operations. This device has a noticeably different topology, where 11 qubits are fully connected, so you can run logic gates between any pairs of qubits. We also have a quantum annealer from D-Wave, currently the 2000 Q solver. Quantum annealers work by returning low-energy solutions of a problem and are well suited for optimization and sampling problems. Finally, we have a circuit simulator from AWS. SV1 is available in all regions where Amazon Braket is available. It's a fully managed high-performance state vector simulator that runs on EC2 instances and is always available. It's a good idea to always test your circuit on a simulator before running it on a QPU. So now that we've seen which quantum devices are available to work with, let's take a look at how you can work with fully managed notebooks. Starting from the Amazon Braket service, there are 3 working sections on the left pane: notebooks, devices, and tasks. I'm going to select notebooks. And you can see here I already have a notebook instance running, but I'll show you how to create another one. First, click on the orange button. And here I'm able to create a fully managed notebook instance by selecting a few simple settings. First, I need to name my notebook, so I'm going to enter a name. Next, I can select the type of notebook instance from the list. Different instance types have different combinations of CPU, GPU, and memory, and are best suited for different cases. I'm going to stick with the default, which is a suitable, cost-effective option. I also have to give my notebook permissions using an IAM role. I can use an existing role or leave it at the default to create a new role. There are also some advanced options to enable root access or add additional encryption by providing a KMS key. My new notebook is now being created, and it already shows up in my list of notebooks. It will show as status pending until it's ready, which can take a few minutes. Then it will change to in service, indicating it's ready to use. Here I also have the ability to stop instances when I'm not using them, and I can also delete them. For users with many notebook instances, there's also the option to search by notebook name, status, and date. Now let's take a look at one of these instances. I'm going to use the one I created. So I can create from here any new Jupyter notebook. It will include the Conda Braket kernel. And I can start working in it right away because everything is already pre-installed. The notebooks also come pre-installed with several examples to get you started on Amazon Braket, from notebooks showing you how to run very simple circuits to more advanced ones. There's a folder on quantum annealing with examples for D-Wave. Following these examples is a good way to learn the functionality included in the Braket SDK. Now let's pull all of this together and show you how to run a quantum circuit on Amazon Braket. We'll use a notebook instance to execute on multiple quantum devices. From the Amazon Braket service page, I'm going to first navigate to the Notebooks section. I'm going to use a notebook instance I created earlier and that is already running. From this page, you could create a new Jupyter notebook, but I'm going to pick one that I've already prepared. So we're going to be looking at something called a GHZ state, which is an entangled state involving 3 or more qubits. It's very commonly used in quantum computing and is often used as a benchmark for hardware, and it's also used in some quantum communication protocols. The key thing about a GHZ state is that it is a maximally entangled state and it has extremely non-classical properties, so it's a great way to start with quantum circuits. The first thing I'm doing is importing some general libraries to plot results. This is optional. Next, I'm importing the Braket SDK modules that we need, and we need to define an S3 location where all of my results are going to be stored. I had created this demo bucket earlier, so I'm going to use that. So this is the quantum circuit we're going to use to define the GHZ state. We need to apply a single qubit gate called a Hadamard on the first qubit, followed by a series of 2-qubit CNOT gates. So let's define this circuit here. We're adding a Hadamard to the first qubit, then applying CNOT gates to n qubits. We can define the number of qubits. I'm going to pick 10 just to start. And when I print the circuit I just defined, you can see this is exactly what we want. This is the same picture as above. A Hadamard gate first, followed by a series of CNOT gates. It's always a good idea to test your circuit on a simulator, so I'll try first on my local simulator, which is running right in my notebook instance, and get the results. You can see I'm getting about an equal distribution of 2 states, 0 and 1. We can plot that to make the results easier to visualize, and this is exactly the distribution that you should expect from this circuit. Now we can also use the AWS Managed Simulator just by changing the device ARN when setting up the device. And this will be especially useful for larger and more complex circuits to get the best performance. But for now, I'm going to keep everything the same, with a circuit to make a GHZ state with 10 qubits. Here we get the results, slightly different numbers, but again, an almost equal distribution. Now let's try with an actual quantum computer. I'll first try with Aspen8, which is the QPU available from Rigetti, based on superconducting qubits. Again, I set up the device, and the only thing I'm doing here is to switch the device to enter the correct ARN. One thing I can also do here is check the device properties. This is completely optional, but gives you more details about the device. You can see here I get a lot of information, including supported gates, we have the connectivity of the device, and we also have the gate fidelities. And of course, you could also find the same information in the console in the device details section, the same way that I showed you earlier. I'm going to define the same circuit with 3 qubits, and then I'm going to run the task, the same way that I did with the managed simulator. To check the status of the task, I can just call the state, and I can see my task was created successfully. Now you may have noticed above, I changed the number of shots to 10,000. A shot is a single circuit execution and measurement. To increase accuracy of the result, you'll need repeated executions for the circuit, so you'll need to adjust the number of shots. It can take a while for your task to run on the QPU, depending on availability and on the queue for that device. But here it ran very quickly. You can see the status has already changed to completed, so we can take a look at the results. So this plot shows you the state distribution for our 3 qubits. We expect 0, 0, 0, and 1, 1, 1 to be the highest peaks, so the results make sense. You'll also notice that there are some extra peaks here as well. The results are not as perfect as with a simulator, which again makes sense. Quantum computers are still noisy machines. Another useful thing you can do is see the actual circuit as was executed by the quantum hardware. By pulling metadata here, you can see the circuit that was compiled. That's going to let me see exactly how the circuit was rewired during the compilation step, and which exact qubits the gates were applied to. Now I can do the exact same thing with a different QPU. This time I'm going to use the one from IonQ. And again, the only thing that I'm doing here to swap the device is change that one line. And then I go through the exact same steps, defining the same 3-qubit circuit, running the task, and here I can see that the task has been created. I can check the status again, and now I can see that it's queued. I could wait for it to complete here, but I can also go back to the console to check the status of my tasks. Here I am in the tasks page, and I get a list of all the tasks that I've run along with their status. Notice that I'm not seeing tasks from IonQ or Rigetti that I just ran. This is because QPUs are region-specific. So if I want to see the Rigetti tasks, I just need to navigate to the correct region, US 1 in this case. And indeed, here I see all of my Rigetti tasks. So now if I go to US East 1, I can find all of my tasks from IonQ. And here they are, including the ones that are still in the queued state. Another thing you can do from this view is click on the task to get more info. Here you get details like status, time it was created and completed, and you can also click on the link, which will take you straight to Amazon S3, and from there you can get your result files and keep working with them. So now you've seen how to get set up with Amazon Braket, create a managed notebook, and use the Braket SDK. You've seen how to define a quantum circuit, execute it on a simulator and quantum hardware, and retrieve your results. You can use some of the example notebooks included in the SDK to guide you as you dig deeper with more advanced examples. I hope you try it out and keep exploring all of the devices currently available through Amazon Braket. Thank you for attending this session on quantum computing on AWS. I look forward to your questions and feedback, and thanks for watching.